So thanks for coming. I see you're the real enthusiasts. Appreciate that. Okay. So today what I want to present you is the Sumcheck Protocol. As you see very dramatically how I picture it in my head. Very epic, and it is indeed. So it is a very powerful tool, an interactive protocol. Kind of underappreciated, and I think, it is helpful. Is a helpful technique that goes way beyond just cryptography. So maybe you'll find it. You find yourself in a situation where you can benefit from that in a different context, or I hope so. So this picture took me like 10 days. No. Was made by the help of some algorithm. At first I quoted which algorithm I used, but then I figured, no, they don't do it either. They don't tell me where their data comes from, and so why should I quote them? But yeah, it was fun to play with the software. Okay, so Sumcheck Protocol. I will divide this talk into two halves. Okay, the first one is about the protocol, and then the second half is about how to use the protocol. The second one will be a bit more math heavy than the first one. So try to really get the idea in the first half. In the second half, it's kind of okay if you just don't get the math in the detail, but get the concepts. Okay. And also, if you please interrupt me. The more you interrupt me, the easier it is for me, because as you know, I'm more used to back and forth than just talking. Alone. Okay, so what is the problem we're facing and we're trying to solve? So let's imagine we have a scenario where a prover wants to convince a verifier that some mu-variate polynomial. What's a mu-variate polynomial? It's a polynomial simply that has mu variables as input. Nothing scary. That this sum over all inputs over some Boolean hypercube, that's what we call it, technically, that the summation over this sums to S. Okay, so if we expand that, you see it's just the combination of all different binary inputs you could feed into this polynomial. So we have 2 to the mu many different summations we have to do here. So exponential in the dimension parameter mu. Keep that in mind. This mu will be the dimension for the whole talk. Okay, so this seems to be a lot of work, and we want to convince the verifier that we did that summing over exponentially many terms. And the question is, can we kind of help the verifier? Can we do it so that he doesn't have to do the naive work? Okay, all of it on its own. Okay, so the Sumcheck protocol here, in essence, is a protocol that reduces a claim of this form into a claim of that form. So instead of letting the verifier compute it on its own, the verifier will find himself in a situation where all he is left to do is evaluate the polynomial once at the random position. This random position is completely determined by the public coins. So the Sumcheck protocol is an interactive public coin protocol, since all messages the verifier will send are just random field elements. They will determine at the end the point where the verifier will have to evaluate it once. And this value E is a product of the interaction between verifier and prover. Okay, so if you stare, what's immediate is that in the naive case, you have 2 to the mu many evaluations. So the runtime in the naive case would be 2 to the mu times, with this I denote time, the cost to evaluate the polynomial once. Okay, so this is 2 to the mu polynomial evaluations, naively. And here we face a situation where we have work to do that is linear in the dimension and only evaluating the polynomial once. Okay, so where this term comes from, this will be the protocol, and you're going to see quickly. Okay, what is it good for? So the Sumcheck protocol is all over the place now, and it's getting more and more known. So you find it also, I mean, it's a key building block in interactive proofs, in practically used interactive proofs, not just theoretical. You're going to see why. And then it's also used for delegation of computation, memory delegation, referee delegation. Though I have to be honest, I don't know what that is. And IPs of proximity. So in error correction codes, Reed-Solomon codes kind of can benefit from this tech, or do make use of this technique. I proved to you some stuff about code words. So, and error correction code is everywhere. And another teaser why this, to give you an idea why this is such a powerful protocol, because just take a glance at how matrix multiplication looks like. Matrix multiplication is also some sum, yeah, over a lot of variables. So to give you kind of a hint that if we can apply Sumcheck protocol in such a case, yeah, then we're everywhere, because matrix multiplication is I mean, basically the one and only job GPU does, in my naive understanding of how a GPU works. Okay, so if we have a protocol that can address such fundamental operations, then yeah. And besides its practical applications, it has, at its very beginning, after shortly it was invented, I will tell you then by whom, shortly after it was invented in the 90s, it was then used for major theoretic probabilistic checkable proofs in complexity theory. So major results in complexity theory were derived using it. So one by Shamir, you already heard of it in the lecture, that proving that interactive proofs, the size of all interactive proofs is as large, or is equivalent actually to the space of all problems that can be solved in polynomial space. And that multi-interactive proof systems, multi-interactive proof system, I always mess this up, is equivalent to non-deterministic exponential time. Okay, so if you have a bit of knowledge in complexity theory, then maybe this tells you something. Okay, that before we go a bit more into the protocol, just let's recap what is a multilinear polynomial. So as I said, it has mu variables. So we're gonna stick with multilinear polynomials, which is a special case of multivariate polynomials, namely in that sense that each variable has no power. Okay, so x1, there will be no x1 to the power of something larger than 1. Okay, no x1 squared and so on. But you can have terms like this. So you can have a factor, so you can have a coefficient that is followed by some product of different variables. So at most mu many, but none of them will have a higher power than 1. Okay. And throughout this talk, I will sometimes kind of concatenate all these variables, and just write the node with a vector above. Okay, remember that. So, and in general, just quickly, a multilinear polynomial has this form, okay? So let's not go too much into detail, but I mean, what we immediately can tell is that a multilinear polynomial has at most 2 to the mu different coefficients, because then we tried every possible combination of variables. So you could kind of imagine that a multilinear polynomial can represent it in some hypercube arrangement, that all its coefficients. So if we say we have four variables, then this kind of would be the space we require to store it. Okay, so 2 to the 4 many coefficients are sufficient to represent it entirely. Okay, but now that we got that, I will tell you the Sumcheck protocol using multilinear polynomial, because it's slightly simpler, but you will then learn that, okay, you can use it for any kind of multilinear polynomial. So let's look at the protocol. Any questions to this point, actually? Yes?
Where the coefficients
Where the coefficients come from? Well, we will see that this is a matter of the prover and the prover only. So the prover has the coefficients. We don't ask now where they come from. In a later protocol, we will make sure that the coefficients have some origin or some sense. But now the protocol as a black box, it doesn't. We don't mind where the coefficients come from. But it will play a very important role then in how we use the Sumcheck protocol. Okay. Well, now at this point, all the prover knows is in what field are we operating. So our coefficients are field elements. He knows the dimension. I mean, it's implicit since he has the polynomial. He kind of knows mu. But here also we give him as input the evaluation sum. Okay. He computed it. Let's say this. He computed it before and gave it also to the verifier, and it's now also part of his own input. It's not that important actually at this point. He could also compute it now, but for simplicity, let's say he has it as an input. So here is the statement we wanna prove, or we want to convince the verifier of, that this S is equal to the summation over the hypercube. And the verifier is given as an input also the field, the dimension, the evaluation sum. And here he's also given the polynomial. But I changed the color because here it's a matter of how you think about the Sumcheck protocol. Many describe it as, let's assume he can evaluate the polynomial only once. Okay, so that this is. But you will then see. For now, just think, okay, he has the polynomial. Why not? But he will actually not need it until the very last moment. So how the protocol works is, in the very first round, the prover sums over the polynomial in all variables but the first one. So see, this is slightly less work than the original claim. Okay, he does two summations. He only lets this variable free, so it's just two summations less work than he has to do for the initial claim. So what will this object be? Who can tell me what's the polynomial that emerges from this operation? What's its degree? Exactly. Yeah. Now this is simply a degree 1 polynomial. The initial polynomial has can have 2 to the n many coefficients, but if he does this, he will be left with some polynomial of degree 1. And so he will send this to the verifier. So how many elements does he need to send? Or how can you represent a degree 1 polynomial? Yeah, exactly. So he could send two evaluation points, or he could send the coefficients. Yeah. So I didn't specify that. Here I sent the coefficients. It makes things easier to put on the slide, but it wouldn't matter. So then the verifier, now think this through with me, because then you immediately get why this protocol is complete. Okay, this will all fit on one slide, on one dense slide. So the verifier now takes this polynomial, this degree 1 polynomial, evaluates it at point 0, evaluates it at point 1, sums it up, and checks if it is equal to the claimed sum. Can you see why this will work? If this claim is true, why this claim should also work out? Yeah? Yeah, exactly. It's the last sum that is missing now is left to do for the verifier. So this is a very cheap computation, 2 evaluations, 1 addition, and then 1 check. Okay, let's assume it passes. If not, the protocol, the verifier will output 0. So let's say the check goes through. Then the verifier samples at uniform random a field element. This is his public message, his public coin, his first public coins. sends it over to the prover. Now the prover does almost the same as before, but now just the first variable he fixes with the random value he obtained. Now he keeps the second variable free and sums over the remaining variables. So okay, so here again he does half as many summations as before. So this is now a hypercube of dimensions from 3 to mu. So this is again much less work as above. And this will result in a new polynomial, again of which degree? 1. Yeah. So will all of them be if we continue with this strategy. And the verifier now does the following. He takes this new polynomial he obtained, the latest one. Also, as above, he now evaluates it at point 0, at point 1. But he also now takes the predecessor polynomial from the round before, evaluates that one at the random point, and makes the comparison. And now try to see why this works out. So how does the first polynomial look like? If you plug in R1 at this position, what are you left with? I mean, it's a bit not so easy to articulate in words what's happening on here in math symbols. But okay, so we have this polynomial, and if we evaluate it at point 0 and point 1 and sum them together, we're going to get this thing here if we fix the first randomness. Does this make sense? Can you still follow? Are you still here? Okay. So, and we continue and we continue. So in the ith round, so somewhere in the middle of our protocol, things going to look like this. So we obtained our I minus 1 many public coins. The prover evaluates now the polynomial at this strictly sinking over the strictly smaller dimensionality decreasing hypercube. Okay, the hypercube loses 1 dimension each time. So it's getting less and less work for the prover. He just plugs in more randomness obtained and sends over this degree 1 polynomial. And the verifier always does the same. He always compares the latest thing he got with the thing he got before and see if things check out. Yes? Yeah, at this point we don't make any assumption about the prover. So to make this practical, the dimension just needs to be small. Okay. If the dimension is not too big, so say log in the statement size, then this will still be a polynomial time computation. But yeah, good observation. So if you do this naively, this would be kind of a heavy overhead for the prover. So there will go some but I'll come to this later. Yeah. So at the very end, and now this is the point. So I personally view the Sumcheck protocol as something that reduces this claim to that claim. Okay. Now the verifier. Now we are in the final round, and the verifier at the very end, what he needs to do is he will check if the last polynomial he obtained, the degree 1 polynomial evaluated at the last randomness, is equal to the initial polynomial evaluated at all points, at the random points. Okay. So here is the one and only time where the verifier needs to touch the polynomial. But since this can be very costly still, most protocols develop some techniques how to also outsource this final step to the prover. In fact, we're going to do this as well in our later application. So it makes actually more sense to see the Sumcheck protocol as a transformation of a claim of this form to a claim of that form. Okay, and then you need to figure out how can we convince the verifier of this claim without having him to do the evaluation of the polynomial. Okay, but in its traditional form, this is also contained in the Sumcheck protocol. So in the traditional form, they give the verifier oracle access to the polynomial. Okay, and that's also what you need to make sense of its soundness. But yeah, so the communication cost is we see is straightforward. We have many rounds, right? We send 2 field elements each time and get 1 field element back. So we have many field elements sending back and forth. The verifier cost, as I told you in the introduction now, is simply a linear in the number of rounds plus the evaluation of the polynomial, if he does it. Yes? Yeah, at most,
so
yeah.
The runtime would also be 2 to the mu. So basically this is like...
Yeah, if he does it.
Compared to the passing the input, it's like nothing.
Yeah, true. And, I mean, but yeah, we
are still exponential, the verifier.
Yeah, if we now go into the details of that is exactly the point, that if we leave the verifier with okay, now evaluate it, then we will not have many efficiency gains, because like you said, this has still 2 to the mu many coefficients. Looking at all of them, then he will be kind of in the order of what the prover does in the first place. Yeah. So so don't take the Sumcheck protocol as is. If the verifier has to do the final evaluation himself, don't see it as it does not give you much efficiency gains. Okay, this is not its primary aspect, and this was the point I mentioned before with a colleague that shocked my world, because I always advertised it as that that it always reduces work for the prover. For the verifier, but in fact it doesn't. Not always. It will depend on some. In particular, if you use a multilinear polynomial, the surprising fact, if you have a multilinear polynomial, evaluating it at one random point is about as costly as summing over the entire hypercube. Yeah, we can maybe later, after the lecture, discuss this. It sounds unbelievable, it shocked my belief system, but yeah, it seems to be true.
Because if you have just a 0 and 1,
yeah.
you just need to add.
Yeah, exactly. And the crazy thing is, over the hypercube, you just need to add. And here you need to do a lot of multiplications. Multiplications appear to be more costly than additions. Yeah, maybe one of the most interesting problems in computer science is why is multiplication inevitably more costly than addition. Okay, but now let's not look at the cost of, let's say he has an oracle, somebody else who does it. The prover cost, naively, and here most treatments of the Sumcheck protocol, they kind of skip that, because now the prover cost is not so easy. You need to go more into the detail. But very naively, like we said at the beginning, it's 2 to the mu polynomial evaluations. But there are many ways to optimize that. And in particular, for multilinear polynomials, it will be just 2 to the mu many operations. Okay, so this is important. Yeah. So is that clear enough? What happened here? Completeness. Yeah, if you kind of followed how the protocol is set up, I hope I convinced you that it is complete. So it says that when for an honest prover, the verifier with any randomness, it doesn't matter what he sends. If the prover is honest, the verifier can just also not send randomness at all. He will accept with probability 1. Okay. Then soundness is now more interesting. So if the claim does not hold, then I will show you that for any unbounded malicious prover, the verifier will accept with probability that is bound in the dimension over the size of the field. Okay, which usually for larger fields is negligible, a term. And here, remark. This is the impressive thing about this protocol, that it's for unbounded provers. It's unconditionally true. We don't have any cryptographic assumptions here. Okay. Yeah. Okay. So yeah. The verifier will accept with some probability. So over what am I referring to? Over which probability? The probability, if you run this protocol, so if you do the probability over all random choices of the verifier, then it will turn out that only this negligible fraction there's only a negligible fraction of bad randomness choices the verifier could make. So the unbounded prover, no matter how much he is unbounded, but still his hands are tied in almost all cases. He can only hope to cheat when the verifier is very unlucky and picks bad random, picks the wrong randomness. Okay, so that's what's going on. Okay, the soundness proof sketch. It's astonishingly simple. It fits on one slide again. So let's have one event that the verifier accepts the false claim. We denote this by V. So even though this is not the case, he will say, oh, I believe you. And then let's have the events we denote EI, which are events that the prover sends a polynomial that is actually the honest polynomial in that round. Okay, so all the prover can do is he can send polynomials. This is the only way he can try to. This is his only communication port he has, by sending polynomials. So there's two options: either the polynomial he sends is as it should be in the protocol I showed you, or it's not. Okay, simple distinction. So we immediately, by the law of total probability, we can kind of upper bound the probability that the verifier accepts the wrong claim. By this term, we say that we condition on the event that in the last round, the polynomial is not the right polynomial, or by the probability that he accepts the wrong claim and in the last round, he sent the right polynomial. Okay. Why is there no equality? Could there be an equality? Be careful. These are conditional probabilities. We would need to kind of scale them down again by multiplying them with the probability that the event happens. Yeah. But I got this up wrong in the first myself. So I thought I'd ask you also. I'm glad you also. Okay, so I will now quickly show you why we can upper bound this term. This term I don't know at this point, but let's look at what is the probability that he accepts, that the verifier accepts, given that the last polynomial is not the correct polynomial. This means, so the event that the last polynomial is not the correct polynomial translates to this statement here. So this is the polynomial he sends. It's not equal to that term. This is what he should be sending. Okay, but he sent something else. And now, in the final check, you remember the verifier sampled some randomness R mu and did this comparison, did this check. Or have somebody else doing it for him. But he runs this check. But since those two polynomials are not equal, we can infer that this check will work out with low probability, right? By the means of, you know it, Konrad? Exactly. Something referred to as Schwarz-Dippel lemma. So this check will likely fail over the choice of any randomly sampled R mu. Okay, then we have the first term bound. So then let's do the same trick as above again. Let's expand this one here, and again apply the law of total probability, throw away the scaling terms, and now look at this thing: the probability that the verifier accepts, given that the last round is the correct polynomial and the second last polynomial is not the correct one. Or the verifier accepts given that the last and the second last polynomials are the right polynomials. So this thing again, we can rather quickly upper bound, namely, again, what do these events translate into? So if the last polynomial is the correct one, we have this equation, okay? So this polynomial the verifier will send will actually represent the evaluation of the correct polynomial at all but the last points. And the second last polynomial the verifier will send is now unequal to what it should be, okay? So, and again, by applying the Schwarz-Zipper lemma, because the verifier will compare those two. He will compare those two, and if you stare at it for a few seconds, then you will see, okay, this is again another case of polynomial identity lemma, because the prover, and this is important, he does not know, at this point, the prover does not know the randomness. That will be, that's why we can apply the Schwarz-Zipper lemma, because to that point, the prover cannot know our mu, so we can make this check. No, wait, it should be R mu minus 1. I think it should be R mu minus 1. Yeah. So this check's going to fail, again, according to the Schwarz-Zipper lemma. And we can continue this process until we're in the last round. And you see in each round, we kind of get, by the same reasoning, we get another 1 over f, Schwarz-Zipper lemma, polybound. So we end up with mu over f applications of the Schwarz-Zipper lemma, also mu applications of the Schwarz-Zipper lemma, or polynomial identity lemma, and we're left with this thing. So this is the last. We end up with the search for, okay, what's the probability that he accepts, given that all polynomials were the correct polynomials. Yeah, do you have any ideas what this could be? Okay, I wrote it. Yeah, it's 0. Why is it 0? Here, the prover, the worst thing the prover can do is be honest in the first round. Because if the prover in the very first round sends the correct polynomial, and the claim is false, then the verifier will immediately check, get that. You see that? So look at the first round. So this claim is false, right? Okay, that we are analyzing something here. So this is not the case. And now the prover does send the honest polynomial, and then clearly this check will not work out. So, okay, a prover that sends is a malicious prover that is honest in the first round immediately shoots himself in the foot and is bound to fail. Okay. So we can bound that term. We know the probability that the verifier accepts in this case is 0, and so we are left with the final claim. Super easy. You can improve the soundness proof, the tightness of this proof even further, but this is usually good enough. Because, yeah, mu will be small in comparison to the size of the field. So, yeah. Okay, that was the protocol and its soundness analysis. Now, just quickly, in general, I just showed you one version that is tied to the evaluation over the hypercube, Boolean hypercube. But in practice, or usually, it's always described as some hypercube that has possibly more than 0 and 1 points. So here we have always 0, 1. So a cube with more side length. Okay, so it can be any subset of the field. Yeah.
Sorry, can you go back one step?
Yeah.
I don't understand why, for example, in the third line, or in the second, we have the win under high, mu, and then in the second line we add the not e. If you are in the case not e mu minus 1, then the prover would already know that it is not. He would already return 0, or, and then it's like then he can't win anymore. Why?
Prover.
Because if the check fails, then he returns 0.
Yeah.
But then we can't be in the case that the prover wins in the next.
No. this check, so this check will happen after he sends the mu polynomial. Yeah. Then the verifier. No. Then at this point, so it is complete. So the prover can send the false polynomial at this round, and so far we don't know what happened before, but obviously nothing that made the verifier reject.
Yeah, but mu is the last round.
Mu is the last round.
Yeah, and mu minus 1 is one round before.
Exactly.
And when we have in the case not e mu minus 1,
Yeah.
then the prover already knows that it is not the case, it is false, right? It becomes false.
No, I mean the prover wants to convince the verifier that the true is false.
Yeah, sorry.
And
the verifier knows it.
the verifier will at this point know still nothing. He will just the moment he will reject is when he gets a false polynomial. At this point, he doesn't have the means to identify that. He will then continue in the next round. He will send one more randomness.
Okay. E is just yeah. Okay,
Yeah. And then in the round that follows, he will get something, and that will contradict the check he then has to do. See, here he does this. He does this check, and that one will fail. Yeah. Good point. So okay, in general, we can have arbitrary cubes. It was a question. Okay. Arbitrary cubes, and we can even generalize this further, but this is not that commonly shown, but yeah, it also works. We can do this. The summation domain can be any kind of high-dimensional rectangular object. Yeah, just to remind you, it doesn't need to be the symmetric hypercube. It can be some crazy n-dimensional rectangular. I don't know how this mathematicians call such objects. Okay, so and also what's important to know is that there's a variant of the Sumcheck protocol which works for univariate polynomials. Yeah, this one has also been used throughout the space, particularly useful in the context of succinct arguments, or in different SNARKs this has been applied. So here you just sum over one dimension. Yeah. It is a variant, so it has some slight different trade-offs. It requires just one round for the prover. The prover will only send one message. However, the prover cost will be different. It will be higher. Okay, that's also for you to know. Then further, it can be made zero-knowledge, meaning that we can devise the protocol such that there is no way for the verifier to learn about the coefficients. We do this usually by blind. So at each round, we send polynomials. The prover is sending polynomials. But the problem is now, since the verifier can extract the knowledge or can learn about the coefficients from if he does that in clear about some properties. But if we blind each message we send, this is kind of the idea behind how to make this protocol zero-knowledge. That the prover will add the polynomial on top, a blinding polynomial on top of every polynomial he sends. Yeah. Okay, and then very important that in some settings, particularly if we reason about multilinear polynomials, Justin Thaler showed that it can be implemented in linear time. So what is the n here? 2 to the mu. So the volume is now this n. Oh, but we'll get to that later. Anyway, what you need to take from this point is that the prover, this can be implemented such that the prover does not have any essential overhead to do. In order to convince the verifier, the prover does not need to do much work on the side. Usually, when he snarks, we showed you, the prover had to do some significant overhead computations on the side in order to also convince the verifier of the correctness of his computation. Yeah. So in particular, this succinct arguments that Georg showed to you, where we do this trick with the quotient polynomial, that we factor out a polynomial. There you immediately you hit the boundaries of the quasi-linear time because you're going to need FFTs for that. So in the ideal case, for these kind of snarks, you still have the prover has some overhead to make this proof of correctness alongside his actual computation. And this can, I mean, even though it's quasi-linear, at some point you're going to feel it. So if the circuit is large enough and stuff, the overhead will become significant. So this is something that convinced many people, this fact that the Sumcheck protocol can be used, implemented without creating overhead on the prover side. And last but not least, it can be made non-interactive without requiring the random oracle model. So it's basically sufficient to assume the existence of collision intractable hash functions, and then you can show that this protocol is sound. So I mean, even though the random oracle is widely accepted and not the worst model we have, it's still cool if you can show things without it. Yes? Good question. Next question. I didn't look too much into the definition of it, yeah, but yeah. But something similar to what we learned. This is where I stopped. I looked at the definition. Okay, it looks similar. Okay. Forgot the details. So short Q&A, because now we're done with the protocol, and now we get to its application. How are you doing? Are you still there? Are you still energized? Should we? Okay. So is that clear to that point? Okay. So how can we use this protocol to get snarks?
Is the protocol now for just 0 and 1, or for like the general case?
What we gonna, the way we're gonna apply it, we're gonna apply it for this 0 and 1 hypercube case, but only once I will trick you and actually have a polynomial that is not multilinear. But yeah, but usually, yeah. Again, the cases when you don't sum over the hypercube, it's very straightforward. If you just sit down and think about it, you maybe gonna figure out even yourself quite easily how to extend it to other summation domains. But in practice, you want to have as low degree as possible because the verifier work increases linearly in the individual degree. So if you have degree 2 or degree 3, the verifier will have to do 2 or 3 times more work. Okay? So that's why we want to usually stick to the hypercube as long as possible, because this is the scenario where the verifier has the least amount of work to do. And also remember, we were sending polynomials in each round. If they have a higher degree, we're sending larger objects, right? And then this larger object needs to be handled by the verifier. So that's why you see what usually everyone tries to apply it with as high dimensions and low volume as possible. I think that, yeah. The volume, yeah. 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 They're completely, you can use the complete identical reasoning we used, yeah. So let's get to snarks, my core favorite topic in the last years. I mean, you already heard about snarks. Georg introduced them to you. So let me try just quickly to remotivate them. So the acronym is zero-knowledge, succinct, non-interactive arguments of knowledge. I mean, we will not go into what the argument of knowledge is. That's some typo, I guess. But yeah, you know, it's a technicality. It allows us to extract, assuming that what the essential aspect, what is most amazing, is the succinctness. Okay, this means that. So what is the scenario? We have a prover and we have a verifier, and the prover says, "Hey, I computed this circuit F with this public input X and my private input W. And I convinced you that my private input makes this circuit output true. Let F be some decider of some NP complete problem. Ideally, then this starts to get interesting, and the verifier will accept or reject the claim. So technically, we are not working with proofs here. I think I already raged about this, that everyone in the community calls it a proof, but the mathematicians would go and yell about this, the logicians, because it's not proofs, it's arguments. Okay, it's what it means that a proof, you can never convince anyone about a false claim. Okay. If the proof is false, it's false. You cannot. It's a deterministic procedure, and it's either wrong or right. In my understanding of definitions, some have and say, okay, it must be at least statistically right. So it's arguments, meaning that if the prover is not bound, if the prover is unrestrained in his capabilities, then arguments don't work, because the prover then always can find an argument that convinces the verifier, that makes the verifier accept, even though the prover has no witness in mind. Okay. Yeah.
So the probability that I can convince or no, that I can cheat is bigger than zero, no matter how small it is. We cannot talk about it.
Yeah. And here, I mean, the intuition why that is the case is those proofs are small, right? They're small, meaning the prover, if he has enough time and resources, he could just permute through all possible proofs, through all bits, run the verifier himself, and say, finally I found a proof, or aka argument, that makes me accept, so I will send it to the verifier. And he never spend a second thinking about solving the actual problem. So this, as soon as you have short proofs, you run into this requirement that you need to make some physical assumptions about the prover. Okay, and why I think those objects are so exciting and should be understood and studied much more by everyone out in the domain of computer science. So here is my three core arguments, and after you studied those objects, Konrad already did, so you can maybe challenge me now already. So my motivation why I think those objects should be advertised is I consider them as an efficient new way to do error detection, as error detection codes that operate now on a semantic rather than a syntactic layer. So, or in other words, you could also say, these are error detection codes. So an error correction codes have usually two parameters. So how many bit flips can I have that I'm still able to detect, and how many bit flips can I have that I'm still able to go back to the original message. So these with SNARKs we cannot correct. Yeah, at least nobody thought about it to this point, to my knowledge. We don't know how to correct an error, but no matter how many bit flips you have, you will very, very unlikely, with overwhelming probability, you will not end up at the new statement. So our statements are now our code words, okay? And we can have bit flips on the statement, and the proof is very short. So if the bit flips are uniformly distributed over this message, so we send the statement and the proof together, okay? And the proof is much smaller, and bit flips happen randomly somewhere, but since the proof is exponentially small, the probability that the bit flip will happen in the statement is much higher, okay? If we say that bit flips are uniformly distributed. And now comes the power, because we know that when we change the statement, but not the proof will not verify. The proof will not be valid anymore, yeah? I mean, these constructions would be useless if you just could immediately change the statement and get and have an accepting proof for it. At least I hope I didn't say this wrong. Okay, so this very powerful, and maybe I want to encourage you to think about this and come back and challenge my belief. No, tell me, this has nothing to do with error correction. You totally got it wrong. And what the hell do you mean with semantic rather than syntactic? Yeah. I'm very proud of this sentence. So my second motivation is they are a generic tool to enforce honest behavior. in any protocol. So, you know, when you devise protocols, you have many rounds, back and forth, back and forth. Trying to prove that this protocol is sound is usually always, yeah, you have fun, okay? It only works in very, very simple cases. If you look at some TLS protocols, So, and with SNARKs, now what we can do is we can enforce that every message the prover sends has a context, namely is created by means the verifier accepts. Yeah, so the verifier kind of can be sure, with overwhelming probability, or that the prover did not go whatever crazy route to trick him. Because we restrict the prover on what kind of computations he can do to derive the message he sent us. So it's very strong to exclude huge class of attacks and vulnerabilities in protocols. Remember that. And thirdly, I think it's currently the best tool we have at hand to address this problem for compliance versus privacy. So what this problem is, you know, we have laws, we have law enforcement, we have regulators, and they make sense. At some point, it really makes sense that okay, you cannot have total privacy. And myself, I was a total privacy advocate, but at some point I understood no, society will also not work. We need to have some means. And this is a very delicate problem to discuss about. How much privacy can we give, and at what point do we need to interfere? Should we make a monetary system where we say, okay, up to 10,000 euros, every transaction is completely private. If it goes above some threshold, there will be some message sent to some money laundering service and so on. It all makes sense, and it should be debatable, and this is kind of the compliance versus privacy dilemma. And SNARKs are perfect candidates to address this, okay? Because I can prove to you properties about my transaction, for example. Now, if we stay in this monetary context, I can prove to you a lot of things without revealing anything beyond that. Okay? So these are my three core motivations on SNARKs. I wanted to spend more time on this because I think now when it gets technical, you can look at it at the slides anyway later. That would probably so. But in practice, these SNARKs are not as we want them to be here. Okay, so we have this little thing here on top. It's called the setup, and we require it from one simple logical reason. So we want or at least this one reason. I mean, look, the verifier wants to do less work than evaluating the circuit. But in order to convince the verifier, if I give you a proof, you need to at least know what the hell are we talking about, okay? So there is some point where the verifier will have to look at the circuit and do a computation which is in the same order as the prover does. But from that point on, the verifier knows what we're talking about. He knows the circuit. He prepares some kind of he makes some cheat book on his side, okay? And from then on, we can. In every interaction have a verifier that is sublinear in the circuit size, or even logarithmic or constant. Yeah. But there needs to be some setup, and the problem with these setups is that they usually are tied to a specific circuit that expresses your relation. You want to argue then later about. And it also takes as input some sectoid randomness. And the first generation of efficient SNARKs, there it was, they termed this coin trapdoor. And that it was indeed because the person who knows the secret randomness with which the setup was run could then always forge false arguments. So completely wreck soundness, okay? So they made a huge effort, some rain dance ceremony, burning laptops in order to make sure that after the setup, the randomness was also destroyed. In the end, it turned out to be useless because there was a total flaw in their protocol. So yeah, they burned, they made carbon dioxide for nothing. But it was a valuable lesson for the community, namely that things always go wrong. No, it doesn't matter how good you, the best cryptographers were involved in that. Yeah, even Edward Snowden took part in the ceremony, okay? So it was all for nothing because the error was on another layer, okay? So this, yeah. It was I think the zkSNARK Foundation. I don't know if they were already the zkSNARK Foundation or ZeroCoin Foundation. Yes, it's some organization around some cryptocurrency. Yeah, yeah. But they had good cryptographers at hand, top men, which know what they were doing, and yet it went wrong. So kind of the lesson for the community then is, okay, we can't have secret randomness setups. And even if everything works out fine and there is no revelation later that, let's say you make this trusted setup once, after 10 years, I come into your protocol and then I don't know the guys who did the setup. So after some time, I will say, why should I trust this system, okay? I don't know the guys who did it. So there will always be doubt. You can't get rid of it. There is no party that everyone trusts, okay? Except if Chomsky would participate, then the world would trust. But I don't know if he has interest in that. So we needed to get rid of this problem with the secret randomness and turned it into a search for SNARKs that have a transparent setup where the randomness is public. In other words, the prover and the verifier can agree on taking the digits of pi from here to there, and then the verifier can do this setup on his own, and the prover can do it on his own, and yet nobody has the secret trapdoor. Okay, this is the must-have. Kind of be careful with SNARKs that don't have this.
When we are talking about secret randomness, does it even make sense that it be random? Like, just choose it deterministically, what would be the difference if nobody knows what algorithm I use to choose it?
That's a tough one. I mean, the point is that you can have bad randomness or a little bit of entropy, and then expand that later. And then that's usually what you do. You start with your initial seed of 200 bits that are plausibly random, and then you expand them. But maybe ask again. What do you?
My question is, like, usually when we use randomness, we do it so at some point I cannot cheat, or I cannot predict what will happen.
Mm-hmm.
But here it's something secret, so why does it have to be random in the first place? Why can I not just, like, I'm the one that does the setup. No one knows how I choose this secret randomness. Why does it have to be random?
If no one knows, then you're kind of already in the domain of random. Because nobody knowing means that from an outside observer, it was not predictable. Your behavior was not predictable, and therefore it's hard to distinguish from random.
Okay, so for me, as the one who does the setup, as long as it remains secret, it doesn't matter what I do.
As long as nobody can guess it.
Yeah.
Which is the definition of random.
Yes, but if I use some algorithm, even if it is deterministic,
Yeah.
and if no one knows what I use, then no one can predict it, even though it is not random.
I think the point here is just the technicality, because I could order my SSH key, I could order it deterministically, but the guarantees for SSH to be secure, or these schemes, is that the key is chosen randomly, because there might be some bad keys, right? And that's just the point of doing it randomly, but per se it makes no difference if I just write down a string and take this as my key, because I will be not so unlucky that I hit one potentially bad key.
Yes, but with SSH, like, I don't know, it's like something that's used in other ways. So if you do it deterministically, you would probably at some point have a clue about how these keys are generated.
If you take the same algorithm for every guy, but if I just sit down and write down a string, then there's no difference. If I use some algorithm which is like random, or if I just use my brain randomness.
which you should not rely on. There are interesting studies on how hard it is to be random.
It's just like, doesn't make a difference.
Yeah, yeah.
Just
So
because the hoops are over the randomness of choosing the key.
yeah. So the point is, can somebody is it possible to reconstruct which bits have been chosen? Okay, and it doesn't matter what your randomness strategy is. If you have bad randomness, but then make your own pseudo-randomness generator to expand them, you tell nobody which pseudo-random generator you yourself invented. Then you kind of added randomness by inventing your pseudo-randomness generator. So there is some entropy in your construction, and you use it to expand your own low pool of entropy, and so you get something that is kind of indistinguishable from random. However, if you would reveal your pseudo-random generator, your new one, to all others, then they could maybe in efficient time figure out what you used to get your secret key, to get your public key and have your secret key and stuff. Yeah, but yeah, I like this kind of questions. Randomness is bothering me since day one. Yeah, now the question is, to make a long story not much shorter, but can we express some claims of valid circuit computation as a sum over some polynomial with low individual degree? Why? Because this is the scenario we need for Sumcheck. Okay? For Sumcheck, we want a polynomial which has low individual degree. And now can we kind of knit into this polynomial some meaning, speaking about some circuit computation? And the ideal candidate, which is the language that kind of helps us to get us there, is often referred to as the R1CS, or rank 1 quadratic constraint system, which looks like this. You have three matrices, A, B, and C, all of dimension n times m. Okay. And you have some vector z. And this z vector is a concatenation of the statement and the witness and the one element. And the statement is in the language if there exists w, which is then part of C, such that this equation holds. Okay, you've seen this in the exercise. This is the entry-wise multiplication. And you kind of can refer to n as the number of, technically it's the number of constraints or equations, but sometimes people call this gates. Okay, and m is the number of variables, which some people call wires. In practice, you're always going to end up in a situation where m is kind of like n. It's very interesting research. It's not that obvious, but usually. So this is how we're going to continue. We're going to consider these matrices A, B, and C as square matrices. So having dimension n times n. Okay, and this is totally fine since most programs are going to end up in this state anyway. And if not, we can kind of nudge them and stretch them to get there. And also, without loss of generality, but to make things much simpler, is we're going to assume that n, also the length of our the matrix, is some power of 2. And here comes this mu again. This will be this is the dimensionality factor we used before. So okay, this language is an NP-complete language, and I already had you play with it in exercise 5. You saw a bunch of compilers that translate something that looks like standard code, but it was usually always a subset of C or a subset of Python, or Socrates feels like a Turing-complete language, but in fact it's not, right? Because you have you don't support dynamic looping and some conditional jump instruction and stuff. So basically, you have a programming language that can always be unrolled as a circuit. Okay. Not Turing complete, but I don't know what the term for that is. But yeah, I hope you remember this from the exercise. And now we have a language which defines. So this is a bunch. These are n equations, right? And each of them has low degree. So kind of smells, this could be where we want to go. A quick side remark, but I also think I also showed you this already in the exercise, that the square span programs, the stuff that Georg showed you in the lecture, have a very similar representation to R1CS. Yeah? Instead of 3 matrices, A, B, and C, you just have 1 matrix. And the condition for a statement to be in the language is this, rather than that. Yeah.
We don't know any system that makes it possible to express Turing-complete stuff, or is there?
Yeah.
It kind of feels like if I could do that, then I could solve the art important or something.
No. But this was my second choice. I wanted actually, well, was thinking to teach you, but show you about, is how to use SNARKs recursively. Then you can get something. You can get SNARKs, or in parallel to SNARKs for circuits, there was this development for SNARKs for machine computations. If you have recursive SNARKs, then immediately you can do SNARKs for a machine computation, yeah, that's, so we already know how to go farther. Yeah. I can, yeah.
I think this was in the lecture of artifact computation, right, where we expressed F as in some arithmetic.
There was a discussion.
Yeah.
When the whole recording between you and
Georg, yeah. Because Georg said that it's Turing complete, and you said, no, I don't think that it's Turing complete because it has to be like finite size of the stuff, and I think this is also the thing which makes it not like prove the order stuff, because we have this. I thought about the order, so.
Ah, cool. Yeah. This is so the point is. So the SNARKs, as they're usually described, and as the ones you saw in the lecture, they only operate for circuits of a fixed size. So okay, but during machine computations, we don't know. So we also want to be able to run computations where we don't know when they halt. Okay, and is this possible? And in fact, can you construct from SNARKs that have a fixed size? Can you kind of recursively, if one SNARK proves the correct, let's say you have a SNARK that proves the correctness of one transition. So you have input is your tape and your transition function, and then this entire circuit does nothing but take those two things and apply the transition function, creates a new state, and outputs the new state. This is one fixed circuit. We can do it. But now we can also make, so we have a proof about this thing, this one transition, and then we put this into the next SNARK, which then, into the next circuit, which will verify that the predecessor step was done correctly, then do his job as a good old Turing machine and apply the next step. And we have a proof output from that, and so this is the way we can create SNARKs for computation that are for machine computations.
But the circuits are, the output from the circuit is not feeded back to the circuit?
Yeah, you use one. You have one circuit which describes two aspects. First, verify a SNARK. Second, apply the transition function. If you have this one unit implemented, then you kind of already can make any arbitrary recursive trees. So, this would be now a line, because you can only then feed it to itself. But what you would want is actually a SNARK that takes two proofs as input, or something like this, verifies them both, and then outputs a new one. So then you can get directed acyclic graphs and do even crazier stuff. So that's super exciting, this development. And yeah, I mean, you can do things like, I can prove to you that the entire history of some blockchain is computed correctly, and give you a tiny proof to attest for this. Because usually, in order to verify that the Bitcoin blockchain is valid, you need to download the entire ledger. I don't know how many petabytes it requires by now. And yeah, you can compress that. It's astonishing. But we have some issues with recursion. We don't know really how to argue about the knowledge soundness. So, because how can you extract from? So how can you extract recursively and stuff? So there's still a lot to explore. This is really frontier of the current developments here. How much time do we have left? Okay. 30 more minutes or less? Yeah, let's try to be quick. But here's the part where I hope you at least to get the rough ideas and then look at the slides. I hope they're self-contained enough so you can fill out the gaps later at home if you want to. So first, one very important tool, also extremely underappreciated, and which was one of the most exciting points for me, or one of the 3 cool things I learned preparing this lecture, is multilinear extensions. Okay, this is nothing but Lagrange interpolation, but in high dimensions. And now it works like the following. Assume you have some evaluation table, mapping some bit strings, mu bit strings to some field elements. Okay, and you want to create an object, a polynomial. So you want to get a bunch of coefficients, a mu-variate polynomial, which agrees on this evaluation table, or in the Boolean hypercube, with the evaluation of the table. Okay, so if I evaluate this polynomial within, let's say this red cube is kind of now my attempt to store. This is the cube in which we store the original data. It's here, it's 0 and 1. Data lies in this cube, and if we evaluate our polynomial, which we could also evaluate outside, but if we evaluate it inside this red cube, our polynomial has to agree with the initial with the function. So you have seen this before for Lagrange interpolation, but now it's just high dimensions. Okay. The way how to construct these objects is also fairly simple if you think about it. It's just so let L0 and L1 be the Lagrange polynomials over the domain 0 and 1. It's just a very fancy way of saying, okay, we have a line. So this L1 polynomial is a line that is 0 at point 0, and it's 1 at point 1. That's why it's L1. It's the polynomial that is 1 at 1. And here also, analogously, L0 is the polynomial that is 1 at 0 and 0 at 1. Okay, so these 2 lines are enough now to give us this complex multilinear extension. Namely, look at this. Let's take the first value of our function table and multiply it with a sequence of L1 polynomials, now each having a variable from x1 to x mu. And now think this through with me. So this L1 polynomial is only 1. If we give it as an input, exactly. So if then here, if we evaluate this polynomial g hat at 0, 0, 0, 0, then this sequence will be 1, because we have a bunch of 1s. If here is anything, that is not all zeros, pardon, but if there is just one, then this or that Lagrange polynomial will be 0, and therefore this entire term will just drop away. Okay. And we do this kind of for every value in our function table. So we specify the first value to be and multiplied with a product of Lagrange polynomials, where we now have the first variable in the L1 Lagrange polynomial, and the following sequence now all the L0s. Okay. So this means if we evaluate this polynomial at 1, 0, 0, then this polynomial L1 evaluated at 1 will be 1. All others, L0 will be 0. And then only this term will remain. Okay? So it's it's actually quite straightforward. We can write this a bit more formal, and it looks like this. And we can write out what the Lagrange polynomials look like. Then we get kind of this object. And this object is also often denoted as the equality function. So which this EQ head is kind of the extension of a function, EQ, that outputs 1 if the two inputs are equal, outputs 0 otherwise. Okay? So this is the formulation we're going to work with later. So this equality function. What I found astonishing is how efficient this can be done. So I cared a lot about interpolation in the one-dimensional case, and I spent lots of time on this problem. And then I thought, okay, then when I got to work with this, I thought, okay, how efficient is it in compared to Lagrange interpolation? Or usually, in practice, you don't do Lagrange interpolation because it takes n squared. Maybe you remember this. We had this one homework where I wanted you to do FFTs. So in practice, you use FFTs. This is the best technique we have to interpolate polynomials in the one-dimensional case. And FFTs in the one-dimensional case still require, under the best circumstances, n log n runtime for n data points. And that is multiplications. So n log n multiplications. The multilinear extension, it seems I've been playing. I didn't find any literature on this. It is, again, a technique heavily underappreciated or not that well documented, it seems. Not many people seem to use it. This I managed to implement in n log n additions. Not a single multiplication required. You look at this object and you think like, what the fuck? There's a lot of multiplication here. But you can do straight line programming to kind of avoid multiplying for once. So this I found amazing, that in high-dimensional interpolation, you get n log n additions, and in one-dimensional interpolation, you get n log n multiplications. But the log kind of remains. So why did I show you this? So first we had this R1CS language. To remind you, set was this vector consisting of the statement and the witness. Our n is power of 2. And now let's look at let's say we have something that is in R1 in R1CS, meaning that this equation holds. We can just rearrange terms. We get something that is kind of familiar, this approach. And now let's do the following. Let's view these matrices as again as evaluation tables, meaning that so they have n times n many values, right? And we can. So n is power of 2, so 2 to the mu. So with mu bits, we can index into the column, and with another mu bits, we can index into the row. So if you give me 2 bit strings of length mu, it exactly tells me where to look at. Okay? So we can view those matrices as functions that map now 2 mu bit strings onto a field element. Is that clear to this point? Yeah? Okay. And the same we do for the vector z. The z vector now is only requires mu bits to index into. Now what we can write is, so this equation is now, if you write it out, it is nothing but that thing, okay? This is just still the equivalent formulation. We're just now writing out what matrix multiplication, how matrix multiplication looks like, and here with our bit strings over mu, we kind of indicate pointing at this is all the columns or some. So this is for all columns. This equation holds, because this is kind of what the Hadamard product does. It also says for for each column. This equation holds. Now we just write it out. Looks a bit more scary, but factually it's just this. And now we can apply the technique I showed you. We can interpolate this stuff. So we have our function tables. We interpolate them rather efficiently and get polynomials, a hat. So with the hat, I will denote the interpolation, the multilinear interpolation. So we get those new objects for all three matrices and for Z. And now by design, so if we now write this equation in terms of our polynomials instead of the function tables, we get an object, we get a polynomial, a multilinear polynomial, but we know something about it, namely that this new polynomial, which is just the interpolation of this one, this thing is 0 over the hypercube, okay, by design, because this equation is always 0 over the hypercube. So this new polynomial is also over the hypercube, it's 0. And now what kind of immediately follows if you stare at it for a minute is that if that is the case, if this new polynomial is 0 over the hypercube, then if and only if the statement is in the language, or if this relation also holds. So okay, so now we found a technique how to take a bunch of linear equations and turn them into a polynomial and getting closer to our Sumcheck use case, right? Because for Sumcheck we need polynomials and not evaluation tables. So suddenly we have a polynomial of low degree, of low individual degree. We're going to discuss this then in a second again. So this was our polynomial f of x, okay? So I just copy-pasted it to kind of remind you of what this scary thing looks like. So let's do our first attempt. Now we know by design that this polynomial was 0 over the hypercube. So this implies immediately that if we sum over the hypercube, that we get 0. Make sense? So if it's 0 everywhere, if we sum over zeros everywhere, we get, again, 0. So and this now suspiciously looks like our Sumcheck case, right? So here we kind of are very close. Now we have some summation over hypercube of some polynomial. Couldn't we now use Sumcheck to kind of let the prover convince us that he computed this thing? Maybe we get the snark from that. Well, not so fast. So the other direction doesn't hold, right? So just and this is the direction. So if you make Sumcheck on this thing, you cannot. So even if you convince me that this claim is true, I cannot infer that this claim is true. But that's what I want. I want to be convinced that this claim is true, because if you convince me that this claim is true, the left-hand side, then I also know that R1CS is satisfied, and therefore, and R1CS expresses our circuit. So I believe you that you have a valid witness. But we can't do that because clearly summing over this polynomial could lead to situations where you terms cancel each other out. So at one point you have 3, at the other point you have -3. Summing over them gives you 0. So you cannot directly make this conclusion. So we need to do just one additional trick. Now let's look at this polynomial. Here we have a polynomial. This is the multilinear extension of the values of f over the hypercube. So we know what the values of f should be over the hypercube. Namely, who remembers? Yeah. So okay, this is so in the honest case, this polynomial is the 0 polynomial, right? Because if you extend zeros, you get 0. Okay, the multilinear extension was similar to Lagrange interpolation. It's the summation over the values times the basis polynomials. So and if the values are all zeros, you sum over a bunch of zeros. The same should be here the case. So okay, now if, as before, if now our polynomial is 0 over the hypercube, then we know that wherever we now look in the entire domain, tau is now from the extended domain, this newly created polynomial will be 0. Because if this is all 0, then we interpolate all 0, then q of x will be just 0. And this we call the 0 polynomial. Okay, so this direction holds. But now also the other direction holds, which is kind of what we wanted to get to. Namely, if this newly created polynomial is the 0 polynomial, this is that statement, then we also learn that f of x must have been 0 at every position. Because if f of x was not 0 at every position, so prove by contradiction, assume this f of x is not 0 at every position, then the interpolation would not give us the 0 polynomial. This means at some point this equality will not hold. So if that's not the case, then this is not the case, and therefore we just twist it around. Okay. But now comes the only one and only theorem I will not prove, but it's very easy. So we say, okay, for all this holds, then it implies that. But this is a big for all, right? So this is a gigantic object. So verifying this this statement is not so easy. Now, but what happens if we sample a random position? We don't look at all positions, but let's sample a random position and then check if this is the case. And then we can show that if we sample it at random, and this is the q of t evaluates to 0, then we know that with high probability, with overwhelming probability, f of x will also be 0 at every point. And now we're basically there. So this means we can apply Sumcheck. Finally, we let the verifier sample and send this tau. So we can apply this theorem. And now engage into a Sumcheck protocol over this claim. Dear prover, convince me that you have some polynomial. Now this we can summarize this as one polynomial, okay? So convince me, dear verifier, that you have this dear polynomial that evaluates to 0 if you sum it over the entire hypercube. And then you're left, Sumcheck does just reduce this claim to that claim, and then the verifier is left with verifying this. If the verifier now verifies this and it accepts, he immediately knows, okay, you had a valid witness. Yeah, just go through all the steps we did. If this point will verify, then the verifier is convinced with high probability that the prover knows a witness. But now the question is how costly is that point? Okay. So no, this is one point. This is the first time we are looking at something. F of y has individual degree 2. Okay. Look at the construction. So here f is the product of some multilinear polynomials. Then you get individual degree. You increase the individual degree by 1. And then you multiply it with this equality polynomial, which also has individual degree 1. So you end up with something that has individual degree 3. This is not how I showed you Sumcheck can be done, but I told you that Sumcheck can be done almost as efficiently as before. Okay. So now the question, what remains is for us to figure out how can we make this check efficiently for the verifier, because then we have our SNARK, basically. And the SNARK where we never needed some trusted setup. At this point, where is the setup, right? So okay, so this thing here, if you remember, this was just the product of the Lagrange polynomials. This thing is the verifier can compute efficiently, so basically in time mu. If you don't believe me, just look at the slides again back, then you're going to see. So this thing can be computed efficiently. But what about evaluating f at some random point? So here, as a reminder, in Tuan, you see that evaluating this as the random point will be terrible. So lots of sums will require exponentially much work in mu. So he would need to compute for every position in the hypercube. He would have to evaluate this stuff and even worse. So A, B, and C is public, right? The verifier knows as much as the prover. But he would also then need to have access to set. And this is something we particularly don't want, because set is our vector that contains the statement and the witness. And the witness, we don't want to show the witness. So the prover, this is a problem a bit. Now, but we can solve it very elegantly, again, by using Sumcheck. This is something that amazed me about Sumcheck protocols. They often apply Sumcheck, and then at some point you're done. So we have those free claims, okay? Computing them on our own would be too much work, as I showed you. But let's again let the verifier tell us what this beast here is. Let the verifier tell us. Let the prover tell us what this thing evaluates to. Let him tell us what this evaluates to, and let him tell us what this evaluates to, by again applying Sumcheck. So now we have three Sumcheck claims about this having this structure. So this is what we let the prover compute it, and now he will engage. He give us this RA, RB, RC, and then we engage in some Sumcheck protocol to check if he indeed computed it as we wanted to. So we will, at the end, again, by applying Sumcheck, we will reduce these claims to claims of that form. You see that? Again, we managed to save the verifier a lot of work. So instead of having to sum over the entire hypercube, we will end up in a situation where the verifier will only need to check this, and that. And then he has those free evaluations. And he has the free if this checks pass, then he can trust RA, RB, and RC have been computed correctly with high probability. And then he can make this above check. So this is what we wanted to check by simply multiplying these scalars. Yeah. So here we still didn't solve this problem with. This will be the next and last step, and then we're done. Are you still with me? It's too much, because a lot of symbols on the slides, and I tend to implode if I see too much symbols on slides. I hope you still kind of at least get the idea. Okay, so one small detail is we can run these three Sumcheck protocols since we do them in parallel. We can run them in parallel, meaning we can reuse the randomness. So this R2 is now the new randomness required to make the Sumcheck reduction. And when the prover and the verifier engage in three Sumcheck protocols in parallel, the verifier can be lazy and send the same randomness. But he needs to wait. So he runs three Sumcheck protocols in parallel, and once he got the first round here, and first round there, only then he can respond. Okay, but this is quite straightforward just to see what we can reuse the randomness here, which is useful. It saves us a little bit of work, but not essential. But, okay, in case you wondered. So now what we are left with is with this claim. And yeah, okay. So what's the cost of checking this thing? And here we have another problem, because to evaluate these matrices, we remember they were of size n times n. So they had lots of coefficients. So if we let the verifier evaluate them, so n was the number of constraints, okay, which is the power of 2. If the verifier evaluates them at some random point, he will take a linear time in n. Why linear and why not n square? It should be n square, right? Because these matrices have n times n many entries. Interpolation will give you kind of as many coefficients, and therefore why not n square? And this is again one of the interesting facts about translating code into R1CS. Those matrices are very sparse. Even though they have size n times n, they usually only have kind of n non-zero entries. And if you interpolate something with n non-zero entries, you will get something that has around n non-zero coefficients, and that kind of saves us here. So this, but still, linear time. We want to SNARK. We want the prover to be sublinear in n. So how can we do this? And now this is the one and only time where we require cryptography. Namely, let's use a polynomial commitment scheme. In our case, an extractable one. Extractable simply means that the evaluation proofs. So I hope you remember this, and that's why we also stressed it in addition and during the exercise. So commitment schemes can have evaluation proofs. So first I put my coefficients in a box, put them somewhere, and then at some later point you ask me to evaluate this polynomial at some point. Since the coefficients are in the box, I cannot change them anymore, but what I can do is now I give you a proof that I evaluated this polynomial at this point and convince you with high probability. Extractable now means that this proof is a proof of knowledge. So the evaluation proof that is a proof of knowledge, meaning there exists an extractor. Or more abstract, that I really know the coefficients. I can only make this proof if I know the coefficients I committed to. So, okay. So technicality, it's not that important now. So here we have kind of, and here is now, I told you snarks need a setup. And here this is where our setup now happens. Namely, so the prover and the verifier, they make a commitment. They set up the commitment scheme, which usually takes time O of n. Yeah. But now this commitment scheme allows you to commit to any kind of multilinear polynomials or these matrices. Okay. We need a commitment scheme for multivariate polynomials, not for univariate. And so here we make a general setup, and then in the next step we make a circuit-specific thing. Namely, this is the time where the verifier really needs to look at the program once. Namely, both the prover and the verifier, they commit to this ABC matrices, which are only program dependent. There's no secret input or nothing. Okay, so this can be done totally offline. This is the one and only time where the verifier needs to look at, do a computation that is in linear time. Or he could also trust somebody else to do it for him. Technically, at some point he needs to do it. And now that we have this setup, so those guys committed to the matrices, what can we do? The verifier wants the evaluation at some random point. They both have the commitment. They both committed to the polynomial. And now we can use the evaluation proof technique. We ask the prover to send us the evaluations at this position and an opening proof, or evaluation proof. I think I called it evaluation proof here. I write opening proof. So now let the verifier do this dirty work of evaluating the polynomial. And we are only left with the task to check now the evaluation proof. Okay? And here, this is just to give you an idea. Those objects, those extractable multilinear polynomial commitment schemes, they exist. These are the most efficient ones in the literature currently. But now, since demand is increasing, you're going to see a lot of improvement there. But they are already very, very good. So if you want to commit to n values, let's take the hierarchs-PC polynomial commitment scheme, then the size of the commitment, so this, the pre-computation step is kind of, gives you something that is square root of n. This is the oldest, okay? So this one was kind of, is has the worst statistics, but a good assumption. Then the prover, now this is also essential. How much overhead does it create for the prover to create such a proof that he evaluated the polynomial? Is also linear. So we have no overhead, no real overhead. Then the proof size is logarithmic. Now we're talking. Here in the hierarchs-PC, the evaluation time is a square root of n. Not too bad. It's sublinear, so we have our snark. If the verifier would verify, instead of having to do n, the verifier would look at this small proof and take square root of n time if we use the hierarchs-PC. But however, look at Dory. Dory is it's much more impressive. Probably Dory kind of is already ideal. I could guess I would dare to say that we can't do better asymptotically. Concretely and with assumptions, probably yes. So Dory kind of has the commitment parameters such as one target field element. So in Dory you use pairing groups. The first one doesn't take pairings, but they do. Yeah, and there you have really log size proofs and log size evaluation time. So this hard work of evaluating these polynomials at some point becomes exponentially less work for the verifier, and with basically no overhead for the prover. Because the prover has to evaluate it anyway. So yeah, good question. SXD, yeah, it is the Diffie-Hellman assumption within pairing groups. So yeah, if you have pairings, you remember that decisional Diffie-Hellman needs to be a bit redefined, because you can always pair elements and then compare. Yeah. But it's basically the Diffie-Hellman assumption for pairings. Yeah. Yeah. So, and now very last step, same as above. So we had this problem. So we solved the problem of computing the evaluations of the matrices by letting the prover do it. So what can we do about this set? We kind of do the same. So here, again, the prover will commit to the witness, but now to the witness only. Okay, this is, and then he will give us an opening proof at the random point. And we can now, and this is the point where the statement comes into play. Here, the verifier will now. I don't get confused. But so okay, what's happening here? We want the statement, if we can blow up the statement to be as big as the witness. So the witness is, let's say the witness is of size 2 to the mu minus 1. And now the statement is usually much smaller.